I think most of you know me, but I'm Pavan Racherla. I'm a second year postdoc with Russia. And today I'm going to talk about, as Mike pointed out, quite a big question. At least the title is long. Can regional climate models provide realistic precip and surface temperature information for continental-sized regions over the course of long simulations? So actually each of those things are important because we're not talking about a small particular region anymore, but a large region and long simulations. You'll see why both these things are important to this talk. So why use regional climate models or RCMs in the first place? To understand why, consider the following statement. More intense, more frequent, and longer lasting heat waves in the 21st century. This is from a paper by Neil and Tebaldi, 2004. Note that this is based on a GCM ensemble experiment. Come to think of it though, such prognostications are quite difficult to trust at small spatial scales when simulated with general circulation models. Besides, the public and private sectors are really interested in higher spatial and temporal resolution for their decision making in any case. So given all this, it's not surprising that regional climate models are being increasingly employed nowadays, and they have the ability to resolve processes and physical features that GCMs cannot, and when constrained at the lateral boundaries by GCM generated data, present or future, they can provide real-time policy relevant information, all while being physically consistent, unlike purely statistical models. So that's sort of where RCMs have come in over the last 10-20 years. But much basic research still needs to be done before wide-scale deployment in order to help better quantify their ability to simulate complex physical processes, as well as their ability to actually simulate somewhat accurately, at least, the present-day climate. One of the papers that really set me off on this path was a really nice paper by René Laprise. He's at the University of Quebec. He really has quite a laundry list of outstanding issues in regional climate modeling, and some of those things really got me interested in this area. So here in this study, I'm going to assess two particular aspects of the model performance. One, the ability to reproduce the climatology for a given time slice, and two, the ability to reproduce trends across two time slices. While related, they're still measuring two different aspects of regional climate models performance. In this case, you really are trying to, you care about details. Spatial details, temporal details are actually important in the first place. Whereas in the second one, details are not as important. You're really thinking about broad scale patterns. Is it able to get precip difference for the northeast US, etc. So they're two sides of the same coin, but somewhat measuring somewhat different aspects of model performance. Very briefly, I'll cover the modeling that I did. We used the advanced research version of NCAR's WRF model, it's popularly known as ARW, as opposed to what's called a non-hydrostatic mesoscale model, or NMM, or they call it now alternately the North American model. But in any case, I used a domain centered over the continental US. You'll see in the maps the extent of the domain. The resolution was 20 cross 20 kilometers with 35 variably spaced layers, signal layers extending from the surface to 100 hectopascal. And then a 2-minute time step, which is consistent with the spatial resolution. And I used only tried and tested physics options. If you're interested in knowing more, I can discuss, but it's really, most people may not have heard of many of those options. But for those of you who do cloud modeling, etc., you should know that I basically used a single moment microphysics scheme. But as you'll see, it doesn't really matter all that much, whether you use single or double moment. But there are many other options which I tuned for doing long climate simulations. And I save diagnostics every 6 hours. So I didn't mention here, I did a 10-year simulation. But 6 hours diagnostics being saved, it's already actually 700 gigabytes. So I couldn't save any at a higher temporal resolution because it takes several terabytes then. So it's just not really It's just too prohibitive to do that. The lateral boundary conditions were provided by the high resolution frequency North American Regional Reanalysis, which is at a 32-kilometer resolution and 3 hourly controlled resolution. I used a 9-point boundary zone where the outermost layer is entirely specified and the next data are neutrally relaxed. And it's important to note that I used no internal nudging, that is, nudging in the interior of the domain, either conventional or spectral. What that means is they're allowing for errors to grow within the domain, so that's important to know.
The North American Regional Reanalysis,
NAR.
What model is used for that?
The NAM.
So it's also, so it's a different version of WRF.
Yeah, sort of. That's true. I mean, I think it depends on which time frame you're looking at. They have a historical reanalysis from 1979 to 2003. They used a different model, I think. After that, they have a real-time climate data assimilation system. I think now they use WRF and MM. So I think it depends on before 2003 or after 2003. But yeah, I see. We're using somewhat similar versions too. I did 2 10-year simulations. One I called Run A, 1999 to 2008, so one 10-year slice, and another 1979 to 1988. This decision to do this time slices was dictated not only by the time frame of NAR, but also the availability of the Model E data during these time frames. They are historically given SSTs, so that's how I chose these time frames. Now, to so-called evaluate or assess the model performance, I used the following data sets. I used the NCEP stage 4 reanalysis to validate the precip. This is based on a multi-sensor analysis that is gauge and radar data on 4-kilometer grids, and it's performed by the 12 river forecast centers. And this is the product that they put out on a daily basis, actually. So it's been available since 2002, as I've noted there. So I have about 7 years of this reanalysis data to compare with my WRF precipitation. And just to note, because radar data is really fickle, every day some manual quality check is done at every river forecast center prior to doing the analysis. So for temperature, I use the station data of the US climatology network. And note that the data only include daily minimum and maximum and not the mean. So I'll have to infer the performance on the mean from the minimum and maximum data. So first I want to start off with the assessment of time slice and climatology, which I do for 2000s because the best reanalysis data that I found was the stage 4 precip data. So I just decided to evaluate this time slice instead of 1979 to 1988. So first, let's start off with the simulated monthly mean precipitation. As you can see, I have 12 different panels corresponding to the climatological precipitation for each month of the year. First off, I just want to, every time people look at this and say, wow, I mean, look at all the richness of the spatial detail, blah, 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 so just looking at all the orographic features, everything, you just feel like, wow, I mean, I feel like happy to use an RCM. So that's not to anticipate myself too much, but that's not necessarily a good thing, as we'll see some of these features that are developed in the model. But it looks, nice, that you have all these details. So what else? So blue, red is dry and blue is, wet. So
these are 10-year means.
10-year means, yeah. So first off, if you look at, if you're familiar with the precipitation over the US, what you'll see is that this simulation does a very good job of actually capturing the annual march of precipitation. For example, around October, November, you'll start to see that precipitation starts over the western US. By around February, it extends all the way down to California. And then it starts to regress. And by the time it comes to summer, there's hardly any precipitation over the western US. on the other hand, you'll see that the simulated precipitation over the eastern U.S. is plentiful all year round. One important feature of precipitation over the continental U.S. is it's really organized by the Rockies. So that's why you have a whole lot of different precipitation regimes organized by the mountains here. You have, for example, the West Coast regime. You have so-called Mediterranean regime over California, which means that it mostly rains in winter and spring. Then you have what's called the continental interior over the Midwest, North, and the Great Plains, etc., where you have pretty much good amount of deal of precipitation year round. What are some of the other interesting features?
Summer monsoon.
Yeah,
Arizona.
so you'll see here that starting around June, the monsoon is nicely resolved. So around July it's the peak. And as quickly as the monsoon arrives, it also pretty much dies off. But you'll see that it does not die off really in the model. I'll discuss this feature later. So that's really, I just wanted to show this to sort of build some confidence in the model precipitation right away. But now all the bad news will start. So I first wanted to look at the differences in precipitation between the WRF and the stage 4 reanalysis. Again, first you'll see that there's gray shading. That's where the stage 4 analysis doesn't have any data. So you'll see that there are all these odd shapes because each of these river forecast centers brings in its own analysis, and they're just mosaic together. So you have these odd contours for the data. Okay, so red means it's raining less than observed on an average, and blue means it's raining more. So what you'll notice right away is I have these three numbers left to each panel on the left side. The first number is the mean bias. The second is the mean absolute bias. So basically, regardless of their sign, I just take the mean of the absolute bias at each location. And third is the Spearman correlation coefficient. The difference with the Spearman and the so-called Pearson correlation is in the Spearman, it gives less weightage to outliers. So basically, it's more representative of the bulk of differences across the domain. So what you'll see that the statistics have shown, and just the general blue color, it's clear that the model overestimates precipitation pretty much year round. And if you see, the mean bias is pretty much exceeding a millimeter per day throughout the year. So you can do the math. So that's over a continental US sized region, 1 millimeter per day is pretty substantial bias, over 10 years. So the details are nice, but there are all these, complaints that start to emerge once you look in more detail. And also the correlation coefficient is not bad, but it's not that good either. It's going from around 0.47 in November to about 0.67 at best in April. So all in all, a little bit of a downer from the introduction now. So there are some other regional features you'll start to notice. Throughout the year, pretty much over the mountain west, precipitation is overestimated, so regardless of the season. On the other hand, you'll start to see some interesting features over the eastern and the central US. It's not always overestimated, so there are some it's a little more complex set of errors, which I'll explain in greater detail. But one thing you'll see is this feature of after monsoon almost. Normally by August, the southwest monsoon should have pretty much subsided, but you'll see that it's got some pretty substantial extra monsoon going on, even in September, even sort of in October. And you'll see that it's related to moisture advection coming from the Gulf, and I'll explain this in greater detail, but there are all these extra sort of somewhat spurious features that you'll start to notice. Yeah.
What's the resolution of the NSAP?
NSAP 32 kilometers. You mean the NAR?
Whatever you're comparing
the
to,
ST4.
stage 4.
4 cross 4 kilometers, like I said in the other slide. So it's really, but both of them are regraded to the same grid. So I regrid stage 4 to WRF. So there's no spatial jump actually. So I'm comparing apples and apples pretty much. So there are more complex features which I'll start to discuss. This is basically, this figure is showing the same figure, but I'm now doing region by region. So I want to just see large scale differences in the precipitation between the reanalysis and WARF. So I have these 9 different regions and months of the year. I basically, my idea in this figure is to see where there's systematic overestimation and where there's sort of sometimes positives and negatives. And you'll see right away that the western US, it's clearly overestimating throughout the year, so that's consistent, and we saw that previously. The most interesting thing is smack in the middle in the Midwest, you have systematic overestimation throughout the year, and so normally people would think, you know, you have a nice domain and you isolate the center and you'll not have a lot of differences between model and observations, but this shows that even smack in the middle, you can have huge differences in excess of 1 millimeter per day. There are some more features that I want you to see. The peak differences occur during the, depending on the prevalent precipitation regime over the region. For example, if you see Pacific Northwest and California, they both have West Coast / Mediterranean regimes. And so the biggest differences occur starting late fall and continue through the winter and early spring. The same with the northern plains. The northern plains is in the continental interior regime, and the peak precipitation there occurs in the summer, so it's not surprising that around the warm season, the beginning of the warm season, you have the biggest differences. The Midwest, again, is the same story. However, what's really surprising is what goes on during the off-season. And that's what we care about to some extent, because if you want to give information to end users about growing season and things like that, you need to at least, by and large, you would expect the dry season to start as expected. Some of these features, and you'll see that that's really not happening. I mean, if you see the die-off of the rainy season, it's pretty slow, for example, on the Pacific Northwest, same over California, and even the Midwest. So what's happening is, depending again on the prevalent precipitation regime, the two things happen. If you have a continental interior regime, you already have a weak annual precipitation cycle, and what these errors are doing is they're basically fudging it out even more, such that you have an even weaker annual cycle. You'll see that over the Midwest. So if you add all these things to the base precipitation, you'll see that the annual cycle is even weaker now. And over regions with a strong and prolonged dry season, you'll see that there's a real delayed onset of the dry season. So now we're getting to the heart of the issues, where you want to provide end users with some information that they could use, and you'll start to see that, well, it's really hard looking at this to say, oh, can I really provide this? Can I really give information regarding when exactly in the future it will start to die off, the rainy season will stop, or all these things are known, maybe a little nitpicking, but they're important for what the end users have asked us. So that's why I'm highlighting some of these features. Over these 10 years, you'll see that there's a lot more complexity, and just for brevity's sake, I'll not go into a lot of detail because it's really complex. But if you have any questions, I'll answer later on that figure. I want to move to another important aspect of what end users look for. And this again goes back to the initial slide about more extreme heat waves or more extreme events. And I want to really understand in this figure how good are these models at predicting heavy precipitation events. This is quite complicated because unlike temperature, precipitation is a lot more localized, and not only in space but in time too. And you cannot say that what's heavy precipitation at one time and location is necessarily heavy at another time and location. So you have to kind of set suitable cutoff limits for what constitutes extreme precipitation event based on season and region. So basically, here's what I did in this figure. I took the WARF data and the stage 4 reanalysis, and I mapped them to the US climatology network that I talked about that I'll use to assess temperature, but they also have daily precipitation data. So at their 1,000 or so odd stations, I basically calculated the 95th percentile of precipitation at a given location and time of year as what constitutes heavy precipitation. I hope that it's clear. So essentially, this is, at some stations you have more than 100 years of data, so that's a very good estimate of what really ought to constitute heavy precipitation at that location. But to avoid comparing apples and oranges, I didn't compare WRF with the station data, but I instead compared WRF against station data and stage 4 against the station data, and I took a ratio of the incidence of heavy precipitation at those stations. So I tried as best to compare apples and apples. So you'll see, first of all, that the color bar goes from 0.1 to about 10 or greater. What that's to be interpreted as is, on one hand, the model is producing 10 times fewer heavy precipitation events at a location to more than 10 times as many events. And so that's a pretty big range. And I haven't even presented the baseline numbers, but you can do the math. And you can see also that by and large, first of all, there's a general qualitative consistency between the monthly means and this. So it's not totally unexpected. But in terms of, can these models be necessarily trusted to provide heavy rainfall events? Well, the answer is it's really, dicey, because you're going from this kind of range to, on one hand, to that. So again, it's sort of, you're having some good comparisons, but they're still up to 3 times higher. So it's not necessarily inspiring a whole lot of confidence, but then again, you're talking about heavy precipitation, so it's not easy to get in the first place. So I want to digress here and put all these results in some context. I want to talk about large-scale error growth in regional climate models. All of you know this, but our regional climate models are limited area models, and they are constrained at the lateral boundaries, unlike GCMs, by certain data. In this case, the North American Regional Reanalysis. And the theory says that typically internal error growth is limited by virtue of this constraint at the lateral boundaries. This has been also, coined as the extended predictability paradigm. However, what this does not account for is that if there are systematic errors that start to develop, whatever be the reason, at a given location, it contaminates other aspects of the model solution elsewhere in the domain. The mathematical theory is quite sound on this. Note that this is much more important for climate mode simulations as opposed to short and medium range forecasts, because climate mode simulations are essentially boundary value problems, whereas short and medium range forecasts are largely initial value problems. So that's why this error growth is really important in climate simulations. Of the many types of error growths that could happen, one really important area is what's called large-scale error growth. Let me explain. The large scale is essentially waves, long waves, which basically the synoptic circulation, to be simplistic. And because you have a limited area model, depending on the size of the domain, some of these long wave trains may not even, may basically extend outside the domain altogether. So let's say you have a domain over the Great Plains alone. A lot of people have such small domains. Obviously the long wave trains are, 2,000 kilometers, 5,000 kilometers, and they're clearly going, the domain is kind of squishing it. It's not even going to resolve that wave train. But I won't go into the details, but why does large-scale error growth, far from being resolved? There are many, actually, I read at least 3-4 explanations, all sounding equally plausible. So I'll give you one explanation. One theory out there is that there are incompatibilities between the model solution and the lateral boundary conditions that produces a sort of interaction between the model dynamics and the lateral boundaries, which essentially alters the large scales of the flow. And to understand more of why that happens, lateral boundary conditions are usually imposed Newtonially. There's sort of an exponential relaxation starting from the outermost edge to the end of the buffer zone. But that sort of Newtonian relaxation basically only dams small-scale disturbances that accumulate in the vicinity of the outflow. But the large-scale ones are not damped effectively. So as time progresses, these long waves basically reflect and interfere within the domain, and you start to get distorted synoptic scale circulations. In the mid-latitudes, for example, it's been shown that wave trains 2,000 kilometers or longer are generally where this most significant error growth occurs. Why does all this matter? It matters because it's not difficult to see. Precipitation being a large-scale variable, it's bound to get affected as a result of these large-scale errors. And as you'll see in the next few slides, it really almost explains the whole of the precipitation errors that we see in the model. I want to just briefly explain this figure. Here I'm showing monthly mean vertically integrated moisture flux as analyzed in the North American Regional Reanalysis. The reason I'm showing this is that essentially when you're trying to analyze flow errors in the large scale, typically you look at 500 MB chart to 250 MB chart, try to compare how it differs from the model circulation, etc., and you can look at different levels and see what's going on. But I could then go on and the whole presentation would get consumed with that kind of analysis. Instead, I want to give a snapshot of what's going on in the column itself, and that's why I show the vertically integrated moisture flux. And since the moisture flux is essentially as close to this precipitation source as possible, it will give us a good idea for what's going on that's causing these errors. Again, this is the unit vector, and as you'll see, it's a very busy figure, so I just discussed some general circulation features. Here you'll see, for example, the North Pacific low, which is most dominant in the winter, and it brings moisture to Alaska, Canada, and the northwestern US. As you'll see here, I may not see it, very bad. But just trust me. There's another stream that goes from the North Pacific. It goes via northern Mexico and provides moisture to the southern plains as well as the southeast. So that's why the southeast also has a nice winter precipitation regime. On the other hand, you can see that the Gulf of Mexico is a principal moisture source throughout the year for the eastern US. Then you have more detailed features that you can see cannot be resolved in the general circulation models or the NCEP global reanalysis tools, things like the Gulf of California, which is essential to resolving the southwest monsoon. So you'll see all these different features that are encapsulated in this figure. But I won't go into too much details, but I'll now show the difference between the moisture flux in the model and not. I want to add a caveat that I'm not suggesting that all these differences are due to large-scale errors only. There could be boundary layer errors at the coastline, things like that, but large component of these differences authors have shown come from the large-scale errors. So they have a strong signature in these differences. Again, this is the unit vector of the difference, and because these are vectorial differences, they're kind of very hard to understand at first glance. You have to have the baseline vector, but I became too big to show anything. That's why I separated those two figures. But you can see some differences right away. You'll see that in the winter, the low over the North Pacific is simulated very poorly. And essentially what happens is instead of moisture being channeled proportionately as in the observations to out of the domain into Alaska and into Canada and the northwest US, you're pretty much because the low is not very strong, you're starting to get most of the moisture advection into the northwestern US. And you can, if you remember the slide that I had a lot of extra precipitation over the northwestern US, you can see now why that's going on, because pretty much throughout the year almost, you're having that feature. As the summer season starts, this low pretty much becomes weaker in reality, and so most of that instead just goes into as far as the Midwest and the plains, the northern plains. So you can see again that if you remember that picture, that's sort of one reason why, even though the Midwest is smack in the middle, you're getting all these 1 millimeter per day extra precipitation. So it's sort of, if you look at one part of it, you can see that it's very much dependent on what time of the year you're in. A lot of people who've explored trying to minimize these errors look at 1 month and start to say, well, we did this will minimize. But if you see the outflow, inflow, everything changes depending on the time of the year. And to situate a domain properly to guard against this is not easy, because it really is a lot more complicated. But that's an obvious feature. Another obvious feature is, for example, the North Atlantic storm tracks. You'll see that depending on the time of the year, you don't, in winter you don't have enough moisture inflow. In the summer you have excessive moisture inflow. So basically what's going on is that depending on the time of the year and the intensity and location of the North Atlantic storm tracks, you're getting either insufficient precipitation or excess over the East Coast. These are obvious looking at it, but there are some really interesting features that look plausible, but really are quite erroneous to start with. If you saw the southwest monsoon, if you see here, what's happening is that normally most of the moisture should be channeled by the Gulf of, by the Great Plains low-level jet into the central US, and at some point it should start going northeastward into the eastern US. Instead, what's actually starting to happen here is that there's some spurious feature that's basically transporting a lot of moisture instead over the Sierra Madre, over North Mexico, into the southwest. July, August, September, October, I know they're not easy to see, sorry, but essentially what's happening is that instead of channeling moisture into the central US, it's basically channeling moisture via northern Mexico into the southwest, and that's why you're getting this extended monsoon kind of thing. This is sort of where you'll start to see these very interesting features that should never have developed in the first place, but they create these scenarios where you think, oh, it does look plausible, but it's really not correct. But there are many other features, but I won't discuss more. If you're interested, I can discuss in greater detail. I want to just wrap up this section with a brief look at the temperature evaluation that I did. First of all, I looked at T2 min, which is basically the daily minimum temperatures, or again 10-year averages for each month. And I compared them by basically a nearest neighbor interpolation. I took the WRF data and interpolated to the station data. Basically, because it's temperature, I also had an altitudinal constraint that if a model point is not within 50 meters of the station, I excluded from this, and also a lot of other data cleaning up. So I pretty much took care of the cleaning up of the data. And here's what you see. Basically, I switched the color schemes from blue means it's colder than observations say, and red means it's hotter. So you'll see right away that it's mostly red, meaning that the minima simulated in the model are not low enough. As much as on an individual station basis, 10 degrees Celsius. So I would advise against looking directly at the station, individual station level, because there's a lot of reasons why you could get such a range of differences given you're directly comparing model with gridded data with station data. So there's a lot of reasons why you should not directly look at this. But I would encourage you to look again at these three values, the mean bias, the mean absolute bias, and the correlation coefficient. What you'll see is that for most of the year, the mean bias is between around 1.5 and 3.5 degrees Celsius. So that's sort of how much on an average the minima are overestimated daily. What's really nice, other than this local feature, too cool is that the error is pretty much uniform. And so that's kind of, from a statistical viewpoint, it means that you can really use this data, just sort of do some simple statistical modeling and kind of get this as close as possible to station data. And that's, you can see in the high correlation coefficients, mostly above 0.9. So basically it's telling that the model is getting the large scale pattern of minimum temperatures, although on an individual station level it's not getting it, with the exception of this feature. And you'll see this continuation of this in the Tmax. On the other hand, on Tmin side you had not low enough. On the maximum side you'll see mostly blues, meaning it's not high enough. So the minimas are not low enough, and the maximas are not high as the observations say they should be. So here you have generally better correlation coefficient actually, but you can see some pretty serious underestimations of minimum, of maximas, starting from about 3 degrees Celsius to about 6 degrees Celsius even. So the maximas are really being seriously underestimated. But again, there's nice correlation coefficients, meaning you filter it through a statistical model and you can get very nice, and I've done that actually, I won't show it here. You'll get nice comparison. However, if you look at what the overall temperature bias is based on all this, I just took the overall temperature bias to be the mean of the minimum and maximum error. So it's sort of an approximation. But what you'll see is that essentially the range of temperature under our overestimations is going from around 5.5 degrees Celsius to around 3 Celsius. So this is generally what's reported by many authors, so it's not surprising. In the analysis, I exclude these 3 regions because the data sparseness is really low. But if you see for the rest of the regions, it's really, really cold to the tune of 5.5 degrees Celsius throughout, the second half of winter and spring. On the other hand, through most of the warm season, you'll see that it's generally within 1 degree Celsius. So basically that's pretty good, except the plains where you have a slight warm bias.
Do you think the WRF model, how does that treat the land surface? So I was just wondering because maybe irrigation. And
yeah, I'm getting into that. Thank you.
Okay.
Yeah, that's a good point. And so I just want to wrap this up by saying that this is mostly what many other authors have seen. So it's again not very surprising because temperature has been evaluated a lot in these models. I want to wrap up this with first part of conclusions. I have a very brief second part, so not to worry. I want to make a general conclusion by saying that obviously RCMs have the capability to generate this so-called high resolution frequency information. But as you've seen, the realism really varies over continental-sized regions. And the end users must use this information cautiously. Using the data straight over New York City or wherever, it's really not advisable. You must really know what you're doing to utilize this data. Again, it's difficult to definitively pinpoint where the model does well, not so well, because authors have shown that if you change the domain a little bit, the whole set of results changes. That's because of how the large scale errors are organized. So I'm not going to go too much into where it does well and does not. However, it seems that precipitation is predicted better over the eastern US than the western central US. I just want to say that it seems to me that the best way to use this data is to spatially average the data. That you'll see by looking at the biases. It's no brainer that they start to become better when you start spatially averaging. Then again, it's ironic because the whole reason of using regional climate models is to get that detailed info. So my suggestion about this seems counter to the whole enterprise, but that's my opinion.
So how do these results compare to GCM?
Yeah. We actually looked at it, and I will contextualize it more, not for the baseline simulation, but for whether they're actually capturing trends. Whether GCMs capture the same trends that observations and RCMs show. In that context, we actually looked at GCM data.
But
so I will comment on that.
Yeah, but you didn't do the regional analysis that you did with the RCM, with the GISS?
Yeah, that's something to do in the, for baseline too. That's a good point. Yeah, I think in the future I'll.
I mean, instead of just like averaging, the stations in each grid point to each grid point level, ensure that there's like local information. So like this station, maybe it's on the sunny side of the hill, and it's consistently, a little bit warmer than the temperatures. Is there local information like that that you could use to make it better?
Let me follow up this question, a question of my own. Must the grid consist of rectangular blocks, or is there some way of depicting the domain in conformance with the features of the land, the geologic and topographic features, westward facing versus eastward facing, so on and so on and so forth?
It's certainly possible.
Is it possible to
It's possible, but if that was, definitely if that was my only project, I would probably start obviously doing that sort of thing. And it's still hard. I mean, if you don't get, you have, what I didn't say is that obviously at a station level there's urbanization. And there have been several papers about what the urban effect does, for example. So and I'll show you how I circumvent this issue in the trends section, which is very brief, but basically it's hard to remove non-climatological effects from station data. So that's why you start to average it out, and that's what they do in the GISS temp analysis, I think. Otherwise you start to run into issues that you really cannot expect the model to resolve. Not only because a model, any grid point is basically a composite of different land types, vegetation types. That has obviously huge implications for how the 2-meter temperature is estimated. On the other hand, a point is just a point. It doesn't care about if 10 kilometers from there it's this vegetation or that vegetation. So you run into real non-climate effects then. And so that's why I think they have chosen to average and get broader information from this data. But I'll go into this. Just I want to complete the second section. Large-scale error growth in RCMs continues to be the biggest impediment to obtaining reasonable precipitation. Popular solutions include periodic reinitialization, about 1 week to 2 weeks basis. People reinitialize it so that you don't allow large-scale error to grow. However, I don't agree particularly with this because if you're interested in RCMs just for atmospheric information, that seems okay. But reinitializing it periodically does not allow soil moisture or anything to really develop. They have very long memory, as many people have seen. And reinitialization really stunts the growth of those features. So I don't particularly subscribe to this. A more recent suggestion has been spectrum nudging of large scales. So this is like conventional nudging, except you're only nudging specific wavelengths generated in the model, particularly the large-scale wavelengths. I think this is much more promising solution, but I think authors have only looked at it at a very short time scale, 1 month or so. I don't think they've looked at what the implications are for really long simulations and whether the nudging parameters can be easily determined in the first place. And for T2 min and max, like I said, it's really encouraging that the spatial correlations are high. I think that's the feature I take away. I think that even though there are large station level biases, it's really easy to filter these data and get end-use output. And that's what I had in my abstract. That it seems to me that this is something that's a lot more usable from an end-use viewpoint than the precip, which has a lot more going on there, but it's not easy to statistically filter. In any case, this is not model. This is not substitute for improving the model. Moreover, we're assuming biases remain constant with time. And like somebody suggested, one thing to try right away is to use different planetary boundary layer line surface schemes. And I think there will be improvements if I try different schemes, for sure, especially some of the local biases. So most people are interested in using these models for climate forecasts. So what does all this mean for climate forecasts? Obviously, I used a very high quality reanalysis, and yet I got different, very ingenious, creative types of errors. Now if you use 4x5 GCM data to actually impose boundary conditions, you can only see what the implications are. Clearly they'll be magnified. It's an open question as to what they mean if you start using GCM and the boundaries. However, it ultimately comes down to the quantity of interest and the nature of biases, whether they're local or large scale, whether they're linearly or non-linearly dependent on other variables. Then if you subtract across time slices, if they're, as I explain next, if you have a nice correlation between the simulated and observed quantities, like for simulated T2, they might not really matter actually. On the other hand, if the spatial correlation is not good, then at a high resolution level, obviously these biases are going to matter because they're introducing features that are not existing in reality. But very briefly, I'm going to actually look at the answer to that question, just a few more slides. I looked at, I won't go into all the data massaging that I did to get this to be reasonable, but I'm basically looking at minima differences, maxima differences, and precip differences across the 2000s and 1980s. In this, again, to avoid running into non-climatological issues, I do these block averages. Because if you look at actual station level data, you're going to see a lot of noise, and you're not going to get much info out of it unless you stare at each point and compare. So this really removes many non-local effects and sort of really tries to reveal the climate signal from these 2 decades. You'll see that in answer to that question, do all these biases matter? Well, not really. If you look at the big picture, it seems that the model gets the minima differences across these 2 decades pretty well. Many subtle features are also captured. The range is pretty much captured. So it seems to me that, well, part 1 answer is not really. However, if you look at maxima differences, you start to see a different story. And this is where I believe a lot of climate skeptics have been complaining. One of the things that, it goes back to the introduction slide, more intense, more frequent, more extreme heat waves. The thing that people imply when they say that is that the maximas are going to get hotter and hotter. That is, the days that are already hot get even hotter. That's the nice narrative that GCMs at least provide. But in fact, what this figure is telling us is that station data is actually revealing a different story. Actually, most of the bulk of the maximas are changing in the cold season. In the warm season, actually, at best it's neutral, or actually there's a cooling. So what that's telling us is that actually the maximas are not trending along with the minimas, but that most of what the observed climate change over the last 30 years has been one of moderation, they claim. And this data does reveal that. However, if models are to be trusted going into the future, you have to get these kinds of features right, to say more intense, frequent heat waves, etc. And you'll see that it's missing in the model. You'll see that smack here, there's all this sort of cooling effect, and you're not seeing that. Basically, if you look at max-min model differences, they're actually trending to the mean. So both the minimas and maximas are doing the same thing. On the other hand, observations are saying there's some physics going on here that's not really well understood. I have a few hypotheses, like clouds and aerosols, but there's speculations why this cooling effect is happening in the maximum. But a lot of food for thought, because obviously models have to be trusted going forward. You have to get these kinds of features. Now the most surprising result in this paper, with all the precip biases that I showed, the trend across the 2 decades is captured really fantastic. I'm really puzzled. I've been wondering for days with Alec and just discussing what does all this mean. You have all these biases, but yet it's getting the range pretty well, many features pretty well. Maybe in the summer, not so well. But honestly, it's really impressive that it got the precipitation trends pretty good over these 2 decades. Obviously, more questions are raised than answers here. First of all, regional climatological trends are captured really well between the two decades. However, the same cannot be trusted, said of the contrasting trends in min and max. Again, like I said, for these kinds of predictions to be taken more seriously, it's important that RCMs, and for that matter GCMs of course, get these kinds of details right. That'll be a nice trust-building exercise. Obviously, it's imperative that we understand the physical mechanisms contributing to these kinds of contrasts in the minimus and maximus and incorporate them into models. The fact that precip are captured quite well despite systematic and complex baseline biases, to me is very surprising. I'm really puzzled because I don't understand, honestly, what's really going on. Obviously, one thing I didn't show is station level data, which really messes the whole thing up. But I think that at one level it's telling us is if you average over the box, it's getting the broad trend right still, even though it's getting station levels wrong. But I don't know, I don't really know the answer to this. At any rate, more than just the mean trends have to be investigated in order for me to say, okay, these models get trends right in extreme events and exceedances of this and this statistic. So this is but it's still, I believe these figures have really made our funders pretty happy. So to see that the trends are captured well, so I'm happy. But I want to thank Drew for his mentorship, overall vision, and his flexibility in allowing me to pursue this stream of research, because I'm on an applied sciences grant and a lot of this has been mostly somewhat basic research, so I'm really thankful to him for giving me this opportunity. I want to thank Alex. I racked his brain thousands of times. We've had many useful discussions and I really thank him. Any questions? Or well?
Does NAR have precipitation data?
Yeah.
So have you tried to validate the NAR against the ST4?
I think the opposite has been done actually. They have validated against something like this. It used to not be called ST4. It used to just be pure gauge data, rain gauge data. So I think the opposite has been done. I did not validate directly against NAR because I was strongly warned against it, that because it's the driving data already,
right.
If you validate.
But on the other hand, you'd want to know if your downscaling is improving it, right? Because you start out with NAR and then you downscale it and you hope to improve it. So you can't really answer that question.
I actually did look at it. I don't show it here. It's the differences between the NAR data and the stage 4 data are pretty small actually. So it's not telling any different story actually. Pretty much the same features. Only some features like over the western US are different. Otherwise,
the NAR assimilates station data.
Yeah, exactly. NAR, the specialty of NAR is that it's one of the first products to actually assimilate precipitation through vertical heating profiles. So, so that's another reason why I didn't do that, because it's the same thing almost to compare, but just to make to have lesser gripes from your viewers.
Right.
I wanted to compare against an
Independent.
unrelated product. Yeah, but it's doing the same thing pretty much.
I was going to ask a similar question. So basically, the NAR bound